how do you teach a robot a task that relies on, well, feel? It's one of the biggest hurdles in all of robotics. Today, we're going to try and answer that by bringing a really fascinating experiment from 2010 back to life, but using modern tools. This is a deep dive into how robots learn, the physics behind their actions, and why checking up on old science is so important for building the future. So, here's the plan. We'll start with the problem itself, which is surprisingly tricky. Then we'll look at the original AI solution, dig into the physics of it all, see what it actually takes to rebuild this experiment in code today, and finally, we'll get to the verdict. Does the original science hold up? All right, let's dive right in. The whole challenge starts with a task that's pretty simple for us humans, but for a machine that can't see what's going on inside a knot, it's incredibly complex. Okay, so picture this. It's 2010, and researchers at Ben Gurion University have this big industrial robot arm. They give it a plastic bag with 5 screws knotted up inside and a simple command: figure out how to shape all of them out as fast as you can. Now here's the catch. The robot had absolutely 0 instructions on how to shake the bag. None. It had to learn the best way to do it completely through trial and error. The only feedback it ever got was a little ding, a reward signal from a digital scale every time one of the screws finally dropped out. So how in the world did this robot actually learn from just that simple reward system? Well, the answer lies in a really powerful AI technique. It used something called reinforcement learning. You can basically think of this as learning by doing, but for a computer. The robot tries something, sees if it gets a reward, and over thousands of attempts, it starts to figure out which actions lead to the best results. Now, this is where it gets really interesting. The researchers didn't just use any old reinforcement learning. Instead of the standard method, where only the very last shake gets the credit for success, they used something called Q-lambda learning. It's a much smarter version because it gives a little bit of credit to the entire chain of recent shakes that led to a screw falling out. This helps the robot learn way faster. But these researchers didn't stop there. It wasn't enough for the robot to just learn the best shake. They also wanted to understand why certain shakes actually worked better than others. They wanted to know the physics behind it. So they went back to basics, like Isaac Newton basics. They built a mathematical model to break down all the physical forces at play every time that robot shook the bag. This let them predict which forces would help loosen the knot, and crucially, which ones might actually be making it even tighter. And here's the key takeaway. The model showed it all comes down to 2 forces battling it out. You've got the tangential force, that's the side-to-side sliding motion that helps open the knot. But fighting against it is the normal force. That's the downward pull from gravity that squeezes the knot tight. The simple rule for success? Your sideways shake has to be stronger than the squeezing force. Okay, so that brings us to the modern-day challenge. This was an amazing result back in 2010. But could we take that original paper and recreate the entire experiment today, but purely in a computer simulation? Now, this is a lot harder than it sounds. You see, scientific papers are just summaries. They're not complete blueprints. They often leave out tiny but super important details, things like friction coefficients or specific software settings that you absolutely need to replicate an experiment perfectly. And this table just illustrates the problem perfectly. To build our simulation, we could pull 11 key parameters like the robot's top speed right from the paper. But we had to guess or make reasonable assumptions for another 10 parameters, like the exact weight of a screw. This gap between what's published and what you actually need is a massive challenge in science. In fact, you don't even have to take my word for it. The documentation for the simulator we're looking at basically comes with its own warning label. It's admitting right up front that how well a reproduction works depends entirely on how complete the original paper was. It's a perfect snapshot of the problem. So let's get to the results. How did this all play out? Did our digital robot, built on this mix of hard facts and educated guesses, end up learning the same lessons as the real one from 2010? Our first big question is all about the AI. The original paper made a bold claim that their Q-lambda learning was way better. Did our simulation back that up? And the results are just crystal clear. That blue line, which is our smarter Q-lambda learning, consistently figures out a better strategy and gets more rewards much faster than the standard method in red. So yep, the 2010 claim holds up perfectly. Okay, that's a huge win for the AI part. But what about the physics? Did our simulated robot independently discover that same secret to untying the knot that the old-school Newtonian model predicted? Yes, absolutely. The simulation data showed that the robot's strategy, the one it learned all by itself, naturally evolved to maximize that exact ratio of side-to-side force over downward squeezing force. It figured out that shaking sideways was the key, perfectly validating that 2010 physics model.
And that, right there, is the real takeaway. This whole process of using modern tools to reproduce and double-check foundational research is just so powerful. It confirms that we're building on solid ground, and it lets us trust and expand on these brilliant older ideas.
Which kind of leaves us with one final thought. We've just confirmed that these AI methods, when you pair them with a real physical understanding of the world, can solve some really complex, messy problems. So the question is, what's next? What other real-world challenges, from folding our laundry to sorting our recycling, should we set them loose on?